Hello and welcome back to Calculus 1, section 5.3 on fundamental theorem of calculus. Our fundamental theorem of calculus has two parts to it. This is a theoretical section where we learn what ties all of calculus together. And the first part, so part 1 of fundamental theorem of calculus, is something that you already have seen, which is the integral a to b f of x dx equal to any antiderivative f of x computed from a to b, which is f of b minus f of a. So this part you already know. It's the way to compute definite integrals. And we had problems like this last time. Say integral from 1 to e cubed of 4 over x dx. That would be an example. The way we solve this is we kick 4 outside. We have integral of 1 over x dx, 1 over e cubed, and that is ln of absolute x computed from 1 to e cubed, because the antiderivative of 1 over x is ln absolute x. So now we get the 4. We have ln of e cubed minus ln of 1. I don't need absolute values now because e cubed and 1 are both positive, so no need for any of that stuff. Ln and e will cancel, so we're just going to get 3 minus 0, and the answer is 12. At the same time, what this means is that the area under the curve is equal to 12 if the function doesn't cross x-axis below x-axis. So I'll just write that. Let's go purple. So this is area under the curve if f of x does not cross under the x-axis. So we have this from before, that if f of x is positive or 0 or bigger than 0, then area equals integral a to b f of x dx. I have to also put here on ab, then there we go, much better. Something really important, and last class we did talk about that sine function, which gave us a 0. If we calculated wrong, we had to split that and get the positive and negative parts separately, and then take the absolute value of the negative part, and so on. So first part of the fundamental theorem of calculus is simply the calculation of definite integrals. And now we go and take a look at the part 2 of fundamental theorem of calculus, and this is the part where we see that the derivative of the integral a to x of f of t dt is equal to f of x. Now this is the big part of the theorem. That's the fundamental theorem of calculus part 2, and this is the core of all of calculus. This will be upgraded later on, eventually at one point in Calc 3 we'll call something fundamental theorem of line integrals, but fundamental theorem of calculus with line integrals, but that's Calc 3. Now, what you have here is simply derivative of the integral is the function itself. You see that this is a lowercase f, lowercase f. So that's the same f, same function. Why? Because derivative and integral cancel each other. And that's the part, because they get to undo each other. Remember that the derivative of x squared is 2x, integral of 2x is x squared plus c. So they go back and forth. If you put the derivative inside the integral, they will cancel. If you put the derivative outside of the integral, they would cancel. Because these are opposite operations. These are opposite operations. Now we can do a quick calculations to show this by calculating the value. Now you can use any variable. In here we're using t, which is fine. We have the derivative, copy that. We haven't done that yet. Now the derivative of lowercase f is the uppercase f, which is the antiderivative. It's in respect to t. And we have to compute that one from a to x. Now we plug in, derivative first. Now plug in the upper limit, which is f of x, minus the lower limit f of a. And now when you apply the derivative of antiderivative is the original function, minus derivative of a number is 0, because when you plug in value a, let's say 3, f of 3 would be some number, so the derivative of that is 0, and we just get our good old f of x. So if you take a look at the two functions, the only thing that is different is the variable, but the function is the same. Right? Function is the same. So you solve the problems quickly with this one if you understand the way to read the formulas, obviously, which is if you have the derivative in respect to x, of the, let's say, integral 3 to x of, I don't know, e to the 4t times t squared dt. Right? If you have something like this, something that you even can't integrate yet, you will be able to integrate this in Calc 2 using something called integration by parts. But you don't need to know any of that stuff now, because simply the functions are the same. The derivative is, the variable is different. So your answer is e to the 4x times x squared. Oh, no plus c, just that's it. No plus c because it was a definite integral. So simply you are copying the function with the variable x, and the reason is the derivative and integral are opposites of each other and they cancel, right? Now to understand that, if you care, you can just write the limit definitions of the derivative, limit definition of the Riemann, right, sum, which is the definite integral, and you will see how they are completely opposite. So f prime of x is written as the limit h goes to 0 of f of x plus h minus f of x divided by h. The integral a to b of f of x dx is given as the limit n goes to infinity summation 0 to infinity, 1 to n of f of xi times delta x, or which is a dx. So now, can you tell me why would these two be completely opposite of each other? Why are these opposite? Why do they cancel each other completely? Yes.
One has division and one has multiplication.
Amazing. Yes. So this one over here is divided, and this one over here is multiplied. So, perfect. And now I'm going to push it. What else?
Is it because one involves a change?
They both involve.
Oh, yeah.
They both involve change. In some sense. What else is opposite? I'm just looking for the obvious stuff. There is the one that is hidden, something with the change. That one is hidden, but...
Is it because, like, one limit reaches 0, one limit reaches 0?
Okay, that's one that's obvious. Good. What else? There is one more obvious, and then one that is hidden.
Is one of them you have subtraction, the top, the other one is solution?
Nice. Subtraction and addition. They are opposites of each other. Perfect. And the one that is hidden involves the change, as you said, delta x. What is delta x equal to? Does anyone remember delta x? Exactly. So you can now pair delta x, right, with a change of subtraction over there, and then up there with the addition. So technically, all of these operations are completely opposites of each other, and the derivatives undo integrals undo derivatives, because they have all of these operations to be backwards. Now, what I'm going to write one more time in blood here, area under the curve equals integral a to b f of x dx only if f of x is always positive. Now, what this means here is graph is always on or above x-axis. So it's okay for graph to, touch x-axis, to bounce off of x-axis, to even be on the x-axis for some time, because that's the area of 0. But what you are not allowed to have is a dip below. And generally, that's where we get some issues, right, with calculation, like with that sine function we had previous class. That's it. I hope you're not disappointed. Bye.